Okay, student. Now we just see the impulse response of the second order system. Now in that impulse response, then we have to form a list. What is the list you have to be identified? When damping factor delta equals 0, this is marginally stable, so we never use this. Okay. But what you are identifying? When delta greater than 1, when delta equal to 1, and when delta less than 1, greater than 0, all these are stable systems. Okay. Now all these are stable. So there may be a chance of utilizing all these things. Am I not? So now what is the question I am asking before we start the second order system? While you are designing a second order system, so 2 points in your mind. One is what should be the best damping factor zeta. This is best, and this one is best. All are best at present because all are stable. But one is out of the list because this is marginally stable and which is very, very close to the instability. We never use that. Okay. So now among these three groups, among this group, again which one is the best? Okay. Among this group, again which one is the best means, now first we want to identify the practical response. So far what we are doing is the impulse response. Can you observe or not? The impulse response consisting only one term. The impulse response consisting only one analysis. That is the transient state analysis. That is the transient response. If you observed or not, then I just give whether it is a first order or second order, whatever it may be, that impulse response is having only one analysis, which is nothing but the transient state analysis. Just recollect what you are doing. Now this is case 1 when damping factor zeta equal to 1. Now what is impulse response? The impulse response is nothing but k into e power minus omega n into t. Now this impulse response, this is impulse response. The impulse response consisting only transient term, have I not? T tends to infinity. Now this is 0. This is only transient term. No steady state term. No steady state term. Now similarly, when damping factor zeta greater than 1, now the impulse response is nothing but k into e power minus zeta omega n minus omega into square root of zeta square minus 1 into t. Now this is the impulse response. Now this is nothing but the transient response and no steady state term, only transient term. T tends to infinity, this value is also 0. Now when damping factor zeta less than 1, greater than 0, now this is the impulse response which is equal to k into e power minus zeta omega n into t sine omega d into t. Now this is the impulse response again. T tends to infinity, this value is 0. This is the only transient term. There is no steady state term. The impulse response, all these are the impulse response of the second order system. This is the impulse response. Impulse response. One more thing I am adding. Stable impulse response. This is the best one. Stable impulse response. Stable impulse response. Stable impulse response consisting only transient term. There is no steady state term. Am I not? Now what is not there? Now this is nothing but steady state term. No steady state term, nothing. No steady state term. Only transient term. So the impulse response consisting only transient term, no steady state term, you cannot find the error analysis. If there is no reference level, there is no steady state term, can we find the error analysis? Can we find the steady state error? No, there is no steady state analysis for the impulse response. I am already giving the 3 points in the first order. That is valid for any impulse response. No steady state term, no steady state value, therefore no steady state analysis. Not possible to find the error and steady state error in the impulse response. And here is the one important question I am asking. Then there are three lists: delta less than 1, delta equal to 1, and delta greater than 1. These are the list we can comes under stable responses or good responses. All are stable. Now, among these particular three group, which one is best? This one or this one or this one? Which one is best? At this stage, you cannot decide it because this is not the complete time domain analysis. Okay, it is only transient state analysis because this is the impulse response. Now, among these three group, among these three values, which is the best suitable range, which is the best suitable value for designing of a second order system? That is possible when you go to the practical analysis. So the practical analysis is nothing but, now you have to apply the practical existing input. Now that practical existing input is nothing but a step input or unit step input. Okay, now the students, now we have to go for the unit step response of the second order closed loop control system, such that you can have a clarity among these three groups which is the best delta, this one or this one. You can easily identify. Before that, you just take a copy of that. Okay. Therefore, there is no steady state term. There is no steady state analysis for the impulse response. And you have to identify one more thing. The transient term is always depends upon the system time constant. Is it right or not? Can I write like this? This is nothing but k into e power minus t by tau. This is nothing but k into e power minus t by tau. This is nothing but k into e power minus t by tau into sine omega dt. Now, the transient response, the transient state analysis is always depends upon the system time constant, because this is nothing but the time constant here. This is nothing but the system time constant itself. Now the time constant, which is nothing but the time constant, which is nothing but 1 by omega n. The time constant is nothing but 1 by zeta omega n minus omega n into square root of zeta square minus 1. The time constant is nothing but 1 by zeta omega n. So that's why omega n is nothing but 1 by tau. This is nothing but 1 by tau. The zeta omega n is nothing but 1. So the transient term is completely depends upon the system time constant, because this is the second order or whatever it may be. The transient state analysis is actual response. Actual response is always depends upon the system parameters, is nothing but system gain and system time constant. Okay, this is the system time constant. Note on students. Okay. Now students, this is a time domain analysis of the second order system. Now among these three groups, which one is best, that we can decide it only when you go for the practical analysis. The practical analysis is nothing but the practical response is nothing but the step response or a unit step response. Okay. Now this is nothing but, now we will see the next one is unit step response. Unit step response of second order system. There we have a steady state term, therefore there is a reference level, there is error analysis, you can decide it which one is best. But here for deciding best, no steady state error analysis here. So now the students, we just see now which group delta equal to 1, delta greater than 1, delta less than 1. Now among that, which damping factor zeta is the best suitable, then we will see for that. Okay. Now this is the second order system. Now apply the input. Now R of t, which is equal to U of t, because now this is the unit step input. No? Now what is R of s? R of s, which is nothing but Laplace transformation of U of t, which is equal to 1 by s. Therefore C of s, which is equal to R of s, is 1 by s into omega n square by s square plus 2 zeta omega n into s plus omega n square. So this is the closed loop control system response after applying the unit step input. So this is the unit step response, right? This is the unit step response. But now we will see one by one because this is the practical response. Therefore, we will start elimination one by one. Okay. Now case 1. We will start with the first case. Damping factor zeta equal to 0. This is nothing but undamped response. Now this is the case 1 undamped response. Therefore C of s, what is C of s? Now this is C of s. C of s, which is equal to 1 by s into omega n square by s square plus delta equal to 0 is omega n square. Now don't do any partial fractions, any sort of thing. You know that when delta 0, pole is on imaginary axis. When pole is on imaginary axis, only sine or cos term, because there is no real part. That you can write directly. Therefore, don't do partial fraction. A value, B value is not required. Now C of s, which is equal to a by s plus bs plus c by s square plus omega n square. All these things are not required. There is not at all useful to us. What we require, then the delta 0, pole is on imaginary axis. Directly draw the response. What is the response? Now the unit step response is the unit step response in time domain. The unit step response in time domain C of t, which is equal to k into sine or cos omega n into t. But there is a reference level, no? There is a reference level, there is a steady state level. 1 minus. Okay. Now minus is the sign I am indicating only for my response is to reach the reference level. Okay. My response is to reach the reference level. Now this is the steady state level or reference level. Now the response is constant amplitude and frequency of oscillations. The response is constant amplitude. The response is constant amplitude and frequency of oscillations. Now, the response is maintained constant amplitude and frequency of oscillation irrespective of the input. Whether you give the input, whether you give the steady state value or not, it not bothering. Now, either we give the steady state value or not, the response is maintained constant amplitude and frequency of oscillation irrespective of the input. System is marginally stable. Am I not? The system is marginally stable, which you already know in the impulse response. The same thing. Only the thing is the same responses, but now there is a reference level. There is a steady state term. There is a steady state level. Now you finally give a final analysis that can you prefer practically a damping factor zeta equal to 0? No, we never prefer practically damping factor zeta equal to 0. Damping factor zeta equal to 0. Undamped response is not preferred practically because the reasons, you tell me what is the reason. One strong reason, system is any response is maintained constant amplitude and frequency of oscillation, system is marginally stable. Never prefer a marginally stable and unstable systems. And the second one is poles are on imaginary axis. When poles is on imaginary axis, time constant is infinity. You know what is the meaning of time constant definition? The time taken by the response to reach 63% of final value. Out of final value, how much time it will take to the 63%? Infinite. Then what is the settling time? Settling time is 5 time constant, let us assume 5 into infinite. Can you prefer any response is having a settlement of 5 into infinite amount of time? Can you prefer any response is having infinite amount of time to reach the 63%? No, we never prefer practically a settling time of infinite. Nobody will give the infinity time to settle in a life, in a response, okay? So we always prefer a moderate settling time, moderate rise time. So because of this particular reasons, then the undamped response is not preferred because margin is stable, time constant is infinity, settling time is infinity, nobody will prefer, okay? Note down this. That is the reason why this is totally eliminated. Damping factor zeta equal to 0 is never used while designing the second order system, okay? Note down this. Okay, now we'll go for the remaining cases, because the remaining cases are a stable cases. This is a marginally stable case, therefore no problem, you can easily eliminate it, but remaining all are stable cases. So eliminating the stable response, so you should have a specific and a good reason to eliminate that. Okay. Now we'll finish these two cases at a time. Case 2. Damping factor zeta equal to 1. Critically damped response. And case 3. Damping factor zeta greater than 1. Over damped response. Now C of S, which is equal to 1 by S into omega n square by S plus omega n, delta equal to 1, S plus omega n whole square. Now this is C of S, which is equal to 1 by S into omega n square by 2 poles, S plus P1, let us assume. Another one is S plus P2. Insignificant pole is not required, or you can take it also, not a big problem for that. Okay. So C of S, which is equal to A by S plus B by S plus omega n plus C by S plus omega n whole square. Now here C of S, which is equal to A by S plus B by S plus P1 plus C by S plus P2. Now apply inverse Laplace transformation. C of t, which is equal to 1 minus some constant into e power minus omega n into t, some constant into t into e power minus omega n into t. Now apply inverse Laplace transformation. C of t, which is equal to 1 minus some constant into e power minus p1 into t. There is no need to take the insignificant pole, or you can take the insignificant poles also, not a problem. Okay. Then here we have just applied the inverse Laplace transformation. Now here you just apply the inverse Laplace transformation. So now you see here, now these are the 1 minus exponential decaying responses. Now let's take it here. Now there is a steady state level, there is a reference level. Now this is critically damped response. 1 minus exponential decaying, 1 minus exponential decaying, all 1 minus exponential decaying responses must and should start at the rest position. Now, and these two responses will reach to the final value, because here time constant is finite. In this response, time constant is finite. Therefore, settling time is also finite. Here is also same. Now in overdamped response also, time constant is finite. Whenever the time constant is finite, settling time is also finite. So it will take a finite amount of time to reach the final value. But in previously, undamped response will take infinite amount of time. So 1 minus exponential decaying starts at rest position and reach to the final value. Now this is damping factor delta equal to 1, critically damped response, and this is the stable response. Next, 1 minus exponential decaying, this is also starts at the rest position. Now delta greater than 1, over damped response and delta greater than 1, this is over damped response and system is stable. Sir, why you are writing like this? How you can know that both are finite time constant, both are finite settling time, so both are reaches to the settling final value within a finite amount of time, but one point you forget. Now here the critically damped response time constant is least. When time constant is least, response is faster. When time constant is least, response is faster. Very fast. See here, very fastly reaches the final value. Now here, now the over damped response time constant is highest. When time constant is highest, the response is slower, sluggish. That's why it will take, the over damped response will take more time to reach final value. The critically damped response is take less time to reach the final value. Now this is the response, am I not? The over damped response will take more time because the time constant is highest, settling time is highest because time constant settling time is completely dependent, and critically damped time constant is least, settling time is least, that's why it will take very less time faster. Okay. Now sir, both are stable. Stable I am saying. So which one is best? So which one is best, that I can decide it now with respect to error and with respect to stability. Stable, all are stable, but with respect to error, see the error and see the performance and you decided in these two which one is best. Okay. So before that you just first take a copy of this. So now the students, you just think, see the responses and decided which one is preferable. One small example I am giving: open loop control system, closed loop control system. Okay, which is very simple question. Forward path gain, only forward path gain. Input is given, immediately get the output fast. Closed loop control system, Input is given, output will not come. Again that output will take a feedback and go to the input side. Comparator will take a comparison and form the error. Again apply to the controller and again forming, again forming, again forming, like this. So it will take some time. This is slower. This is faster. This is slower. But which you prefer? A open loop control system or a closed loop control system? You are saying closed loop. Oh, how? This is closed loop control system is slow, no? Open loop control system is fast. But why you prefer closed loop control system rather than the open loop control system? Yes, because speed is not the important criteria. This is accurate. This is accurate. Error is minimum. Accurate means here no error analysis, no error calculations, because immediately you give the input and you can get some output. You give the input and you can get some output, that's it. You give the input and you can get some output. Now students, what I am asking is, so speed is not the important parameter to judge the system. So you have one point here I want to identify. That point is nothing but speed is not the parameter, to judge the behavior of the system. Then what should be the important parameter to judge the performance of the system? Students, remember from the first day onwards I am saying to decide which one is the best system. Now there are two parameters. First, it should be stable or not. First you will check. Stable, stable. Second one, now where the error should be less, that you have to be preferable. Understand or not? First it should be stable and second criteria is to be accurate. Not the speed. Speed is not the important parameter to decide. If speed is important parameter, we always prefer open loop control system rather than the closed loop control system. That's what I'm saying. Now, speed is not important parameter. Again, if the speed is not the important parameter, the overdamped response is having highest time constant. Whenever the overdamped response is having highest time constant, which means it is very slow, too much slow, very slow. This is very, very slow. Never prefer such type of a slow response. Okay. But if you compare here, the time constant is least for the critically damped response. This is very fast. Very, very fast here. But one important point you have to be identify, this is a stable response. Now this one is a stable system. I am talking about two stable systems, am I not? This is the critically damped response, which is a stable response. Now this is the overdamped response, which is 100%. This is a stable response. I am comparing two stable responses, my dear students. You just observed. Now I put a computation on the two stable responses. This is the stable response. This is the stable response. But this is very, 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 very slow. This is very, 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 very fast. And fast is not the important parameter to judge. And I want accurate. Now how I can find an accuracy? Now accuracy is nothing but not with respect to speed. Sir, we will wait some amount of time. But what? Because here we will wait for some amount of time. Even it be slow, this is preferable. Why this is preferable and why this is not preferable? Because of this particular accuracy. Even it will take, I want finally an accurate output. An accurate output is output where error should be minimum. Sir, you are saying this is slow, this is fast. Is there any other stable performance which will have features, characteristics in between these two? Yes, one response is having, because the underdamped response whose time constant, is not very high and not very low, is a moderate, is a under, is a medium, is a moderate between the over-damped response and critically damped response. Therefore, now this fellow you neglected because of very slow. This fellow you neglected because this is very fast, but what should be the accuracy? I don't know the guarantee of the accuracy, because without measuring the error analysis itself, this fellow is immediately reaches to the final value. So I want finally an accurate output. An accurate output is output. The response should reaches to the final value when error should be minimum or least. Understand or not? Therefore, you have another choice. Greater than this, less than this. One response is having a time constant in between these two. So we will go through that response, and after that we will decide it. Now that one is best or this one is best, we can decide it. Okay. So this is the reason why now this is the reason why this is the important reason such that they should be neglected, and this is the important reason and it should be also neglected because no guarantee of error here, no guarantee of error, and this is too much slow. Okay, this is the reasons why now even if it is a stable response, this is a stable response, this is stable response, even it is a stable responses which we are not used practically. Okay, note down this. So now the students, now finally I want a time constant, not this much and not this much. Therefore, one stable response is maintained a time constant in between these two, and that is nothing but the under damped response. The word under, now it is whose time constant is medium or moderate compared with these two. So that is also you are not finally decided that is the best. That you can decide it after looking its response. Finally, it will be producing an accurate response or not. Of course, it is stable, but accurate or not, you have to be identified. Now, this is the system. Now, the case, last case is available for us. Now, the case 4, I think. Now, the damping factor zeta is less than 1 and greater than 0. Now which is under damped response, whose time constant is moderate or medium compared with these two. Now the transfer function C of S, which is equal to 1 by S into omega n square by S plus zeta omega n whole square plus omega d square. Now partial fraction, all these things are not required. I will write the answer directly, right? Now see here. Now the unit step response of a second order closed loop control system in time domain C of t, which is equal to 1 minus k into e power real part. What is the real part? Minus zeta omega n into t sine or cos imaginary part sine omega dt plus some theta. How to measure theta value we will see later. Okay. Now this is the k into e power minus zeta omega n t real part sine or cos imaginary part. What is theta and how to measure that we will see. Okay. Now first you draw the response. How the response? Now you know 1 minus exponentially decaying. Now this is the response, unit step response. Now exponentially decaying and mirror image. Exponentially decaying and mirror image. One minus exponentially decaying. Now all 1 minus exponential decaying starts at the rest position. Now in the common area, the frequency of oscillations. Now see here. Now this is the reference level. This is the steady state level. That is the reference level or steady state level. Now with respect to steady state level, with respect to reference level, now this is the actual response. Exponential decaying and amplitudes are decreasing. Therefore that is a damped frequency of oscillations. But now students, if you observe here, the deviation of output from the reference level is nothing but error. If you observe here, this is the error at t1 seconds. This is the error at t2 seconds. This is error at t1 seconds and t2 seconds. Then the error is slowly decreases and the response will reach to the final value with a zero error or not. So this type of output is called as an accurate output. Okay, we'll continue. First you take this one.